Alright, so let me explain what's going to happen next week with the midterm exam. Okay, so the midterm exam is next week. It will start at 8:30. Okay, so get here by about 8:20, 8:25, and if you come at that time, don't come into the classroom. I'm going to lay out all of the exams onto at desks, and then I'll let you guys come in, and you will sit down at a desk where there's an exam, and you will take it. Okay. I will provide the exam, which is for you to write on. I will provide the Scantron and any kind of reference tables that you'll need, because today we'll talk about some reference tables. All right. What you need to bring is you need to bring a calculator. All right. So none of this calculator nonsense that happened today. Okay. If you come without a calculator on the day of the midterm, I'm just going to say sorry, you're out of luck, and you're just going to have to go without. Calculator, bring a pencil, bring an eraser, okay? And you are allowed one sheet of paper with notes on the front side only, okay? And that's it. So no scratch paper. You should be able to do almost all of your work on the exam itself. If for whatever reason you write huge or something, I will pass out scratch paper to you, okay? I will provide the scratch paper to you. But just because there's been incidents in the past, okay, I keep track of how many sheets of scratch paper you take, and I need that many sheets, the same number of sheets of scratch paper back when the exam is over, okay? Yeah, I know it's like I've got to be super, like, the boss overlord or something, but it's just, it's true that a few rotten apples spoil the whole barrel, so that's just how it's going to work. From 7 to about 8 o'clock, from around 7 to maybe 8:10, or yeah, we'll just say 8 o'clock, I will have like an optional review session here, okay? So I will not have traditional office hours during my normal office hours time. So normally I have office hours from 5:30 to 6:30 each week. I will not have that next week, okay? What I will have is from 7 to 8, like office hours in here, okay? And whatever questions you have, I will answer them, okay? The only questions I will not answer is this going to be on the midterm? Do I need to know this for the midterm? I won't answer questions about the what's going to be on the midterm, but any questions about material or how to do something, I'll happily answer that. Okay? Are there any questions on how this is going to work? Yes.
So the way you formatted the quizzes, is it going to be a similar way that you do the midterms?
The midterm exam is going to be about 25 multiple choice questions and maybe about 3 or 4 free response questions, okay, in a similar form as the quiz. So the quiz is, you get 3 or 4 free response, and so the midterm will have that, and it will have about 25 multiple choice. I think multiple choice accounts for about 75% of the exam, and the free response accounts for about the remaining 25%, okay? It's going to add up to a total of, I think, 110 points, so there's 10 bonus points. Yeah.
But the way sorry, I didn't finish. The way you word your sentences is similar to the way you word them in your quizzes, like the same. Or is
I think so. I mean,
because
is the way I word them
good?
Fun?
Yeah, it's good. It's clear. So I just want to make sure your midterms are also.
All right. I mean, I try to be as clear as I can. This is it's a statistics class, not English literature. But everybody always complains that someone's always going to complain that the wording was funny and they didn't understand the question. But that's going to happen no matter what I try to do. Okay, so and I don't think that's my fault per se. But, yes, Daniel.
So it would be similar types of questions?
I'm not sure what exactly you mean by that.
If we study the past quizzes, those are going to be this.
So that will form a good base of knowledge, okay? But basically, anything that we've covered is fair game. Okay, so it's going to go from day one to the stuff I covered today. Okay, and I also, just like for the quizzes, I kind of list off the topics you need to know. Same thing for the midterm. Okay, I list off all the topics that you need to know. Pretty much all the topics we covered, but I go into detail about all the topics, and I mean, in my opinion, I think I'm very fair and generous in that I tell you what the quiz is going to cover, and I cover it in a straightforward manner. I'm not trying to stab you in the back or anything like that. So I feel like I give you everything you need to succeed. So, but I don't know if there's any questions about anything. Yes.
You get 1 page of notes?
You get 1 page of notes, okay? And it can be typed or handwritten. Yeah. So.
And the review session, is it per student you're helping, or generally like?
It's going to be like this, okay? Except instead of me talking, or I mean I'll be talking, but you'll be asking me questions. Okay?
And you'll be doing it on the board.
And I'll be doing it on the board for everyone. So if you come on time for that, all right. So what happens is students, because I say it's quote optional, students will trickle in later and they'll ask the same question that someone asked 30 minutes prior to them, and I'll say, sorry, I've already answered that question. Okay, so.
And the notes is 1 page?
And the notes is 1 page on the front only. Okay, for the final exam, you can write on the front and back. Yes.
A little different topic. Labs. I'm having an issue uploading the labs on Mac.
So you don't need to. I mean, I'm not sure what you mean by upload.
I can't print them out either.
Okay.
Last week I was able to, but this week I can't lift it from the.
Yeah.
Okay.
Just do a screenshot.
Okay.
Oh,
You can always.
All of it on a screen.
I can't get all of it on it. Yeah.
Do
Okay.
two.
So I mean, even if you can't get okay, so I know sometimes, yeah, just do your best, all right? Take a screenshot of what you can, all right? If it looks like you put forth a good faith effort into it, you will probably get full credit, okay?
Okay.
If you're just turning in, sometimes people just turn in handwritten things, and I don't know if I can give full credit for that. If you're missing all of if there's no pictures whatsoever, maybe I can't give you full credit.
There's only one more left.
Yeah, there's really only one more after this.
I didn't print the screenshot because.
Okay, that's well, I'll take a look and I'll use my best discretion here. Okay. The homeworks are there to kind of just pad your grade for the exams. Okay. All right. Joplin quiz, not a test. Yeah, so there's 4 quizzes. I take the top 3, okay? But I'll be honest, the quizzes get harder as they go. All right, so the first one's usually the easiest, and then the 4th one's generally the hardest. I think that they get harder as they go. So we'll see what happens after the midterm exam. Okay, I'm not trying to like threaten you or scare you or anything like that, but every quarter, sometimes the midterm exam serves as a wake-up call in terms of either maybe you're just not understanding the material, or maybe you're just not putting forth enough effort. But with this path that you're on, I don't think you're going to pass type of thing. A few students will feel that way. Okay, many of them aren't even here, so I don't feel bad. Okay. All right. So today we will go into chapter 6. Okay, and then in case it wasn't clear, I did not put this up here, so this is not mine. So this is all on probability distributions. Alright? And a probability distribution is like a model of a random experiment. And so it's, just as if you were building a model airplane or a model toy, it serves to represent what a model airplane serves to represent an airplane. It of course doesn't have all of the intricacies of an actual airplane, but it serves as a model. It gives us a good idea of what an airplane should look like. Okay, and a probability distribution, okay, serves as a model of what a random experiment should look like. Okay, and so, for example, okay, so let's before I go on into an example here, all right? And most often our random experiments are created in such a way to have just numeric outcomes. Okay. And these numeric outcomes, sometimes we'll call them random variables. Okay. Okay, so a random variable is the outcome of a random experiment, but a number. So here's a random experiment. And this is going to be flipping a coin. Okay. But the outcome, we're going to set it up so it's a number. So rather than saying heads or tails, okay, the outcome, if it's going to be numeric, should answer the question how much or how many. So the outcome is how many heads did you see? Did you see after flipping a coin once? So if I say, it's an awkward way, but it feels awkward, but this is a totally legitimate way of getting the outcome of a coin flip, right? I say, flip the coin once, how many heads did you see? What are your answers going to be? 0 or 1. Okay, you either saw 0 heads, which means the coin landed tails, or you saw 1 head, which means the coin landed heads. Okay, so the outcomes, possible outcomes, 0 or 1. Okay. So to represent that this is a random variable, maybe we will create what we call a probability table. the outcome, or x, the random variable x, or answering this question, what are the possible answers that x can take? 0 or 1. Okay. It's a probability table because we have the outcomes over here, and then over here, I'm going to ask what's the probability of getting this particular value x. Okay. What's the probability that I see 0 heads? 0.5. What's the probability that I see 1 head? Okay, not 50, but 0.5. Okay, 50% is allowed, or 0.5 is allowed, but again, 50 would not work because it's a number greater than 1. All right, so this is the simplest example that I can think of for a coin flip, and I hope is this okay? All right, so we just have to set up our random experiments so that they have numeric outcomes. Okay, and so we can also say okay, so here's another example. It's a little bit more complicated. All right. Okay, so let's say the probability. So if a woman is pregnant, let's say that the probability that the child is going to be a girl is 0.5. Okay. It's actually closer to 0.49. Did you know that? Just over all of time, boys are born at around 51% and girls are born around 49%. Just
Fun fact.
fun fact. Now you know. Okay, so let's say the probability of a girl is born is 0.5. Okay, let's say there's a couple, and let's say the mother is really intent on having a girl, and she says, I'm gonna keep having kids until a girl is born. All right, then it's kind of like the reverse of what they had back in England with King Henry VIII and things like that, right? So let's say a couple decides to have as many children as it takes until they give birth to a girl. Until a girl is born. Okay? So again, this is a probability distribution, so it's a model, right? So according to this, right, what's the max number of, according to this theoretical model, potentially they might have 100 children and never have a girl, right? Okay? But physically, it's not possible for a woman to give birth to 100 children, okay? I think the world record ever is like 60 something, okay? And that
Live birth?
Huh? Live births, and I think it was all
No C-section. Not
like there were multiple births and all sorts of things, but I mean, if you hear 60, you're just like, that's yeah, one woman, right? So this is just.
Most of our great grandparents probably had like.
Yeah, you know, a lot of, you know, a few generations back, you know, your parents or your grandparents were one of 10 children or something like that. Okay, that was not too uncommon. All right. Well, anyway, okay, but let's. So this is a model, and so according to our model, we might see numbers like something ridiculously huge. Okay, but of course we know real life is not always going to be like this. Okay, so a couple decides to have as many children as many children as it takes until a girl is born. Okay, so this is weird, but let's try to think of the probabilities that that we might see, okay? So what's the fewest number of children that this couple could have? One, right? So here are the outcomes, okay? So let's think of the outcomes, all right? And X is going to be just the number of children that they need to have until a girl is born, okay? So 1 means the first child was a girl, okay? All right, so let's just talk about what this means, and this is, I guess, the situation. Okay, and then most of your probability tables will only just have the outcome and the probability, but to kind of explain this, I'm putting in the kind of the situation of what happened, okay? So in this case, it just means the first child that was born was a girl, okay? So what's the probability that the first child was born was a girl? 0.5. So this is the probability of getting X, okay? All right. What if it takes 2 children for the couple to see until a girl is born? What happened in this case?
She had a boy first.
She had a boy first, and then she had a girl. Okay, so what's the probability of getting this situation?
0.5 times 0.5.
Yeah, I should have actually made this more interesting. Will you forgive me if I do this? Okay, so instead of 0.5, let's put 0.49. Okay, let's put 0.49. Okay, so the very first number is going to be what?
0.49.
0.49. Okay. All right, so this for this situation, how do we get a boy first and then a girl?
151.
Yeah, so in this case, probability of a boy, so in the same way, probability of a loss is 1 minus 0.49, 0.51. What's the probability of having a boy or girl? 1. 1. Okay, so what's the probability of a win or loss? 1. Huh?
It wasn't a test.
I thought one
Yeah,
was
that was
on
on
the-
your quiz.
yeah.
All right, so in this case, the probability is going to be 0.51 times 0.49. Okay, so 0.2499, thank you. So just about 0.25.
So 0 point.
Okay. Is this is okay so far? Anybody having problems? Okay. What if it takes a couple 3? Well, then what happened? It means they saw boy, girl. Okay, and that would be 0.51 squared. Okay, because 2 boys times a girl. All right, and that's going to give you some number, and so on. 4 means boy, 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 girl. And what would I have here? 0.51 to the 3rd times 0.49. Is this okay? All right, and then I'm just going to round off to around 3 decimal places. So this isn't exactly accurate, but I'm just rounding off to 3 decimal places, and it's like something like this, okay, to 3 decimals. All right, and so on, and the numbers keep going on, okay? So we can build up a probability table like this to simulate or to model a random experiment, okay? We can represent these with graphs as well, okay? And so for this one, with a probability table of 0 or 1, our graph, okay, we would have 0 or 1, and then on the on the x-axis we have our outcomes, okay, because our outcomes are x, and on the y-axis we've got the probability of x. So here, if I graph this, both of these numbers have a probability of 0.5. Now, normally we would just put dots, but for whatever reason, whenever we do probability distributions, we draw lines. Okay. Well, when we have probability distributions of discrete random variables, I'll talk about this in a moment. Okay. So if our outcomes can only take on certain values, okay, certain values, like we don't have decimal value type things, okay, You're not gonna see 0.3 heads after one coin flip. You're not gonna see, it won't take 2.4 children to have your first girl, okay? Or 2.46 children, okay? Those are discrete, okay? And in this case, if we were to graph this, I would start off at not 0, but 1, 2, 3, 4, and it actually keeps going on. And the first one, 0.5, the next one's at 0.25, and then I just, I don't know. The first one, probability of about 0.49, so that goes right up there. Probability of about 0.25. Probability of about 0.125. Probability of about 0.062, and so on. So,
So the bottom line represents only the number of children, not if it's a boy or a girl.
right. It only, what is x again? What is an x the answer to? This answers, the numbers here answer what question? How many children did it take until they got their first girl? Okay? How many children did it take to get their first girl?
So it seems like it's 2. 2 children.
Okay, I'm sorry?
So it would be 2.
The answer's not 2, okay? It could be. So let's say, all right, so this seems a little, not weird, but just maybe this is not your typical family, right? This is not usually the way they decide how many children are we going to have, okay? But let's say there were multiple families out there, okay? Let's say for whatever reason it's very fashionable or very desirable to give birth to girls, and families they adopt this mentality. They're going to be like, I'm going to have as many children as it takes until I see until I give birth to a girl. And this happens, and then what this represents, okay, is that some families will just have one child. Some families will have 2 children. Some families will have 3 children. Some families will have 4. Some families will have many more, okay? And this represents, what's the probability that a family will have only 1 child? Or what's the probability that a family will have 3 children, or something like that? Okay, if they adopt this decision-making strategy for the number of kids to have. All right, so this is a model of how to answer this question. All right, is that okay? All right.
So what's the answer then?
So the answer is, there is no answer, right? If I flip a coin, how many heads will you see?
1.
0 or 1.
Yeah.
There's no answer, okay? Half the time you will see 0 heads, half the time you will see 1 head, okay? If a family keeps having children until their first girl is born, how many children will they have? We don't know.
So
okay, it's going to be either 1, 2, 3, 4, 5, 6, or all the way up to 100. Okay, well at some point they're going to have to stop. But
isn't the answer considered either or, like a 1 and the other?
no. So I think this concept of a random variable. It's not these. They're not infinite. It's just these are not solid answers, right? If I say here's a coin and I'm gonna flip it, and I say, will it land heads or tails? You cannot tell me. Nobody can tell me with 100% accuracy whether the coin is gonna land heads or tails. Okay? And all I'm doing is I'm changing that question from is it gonna land heads or tails to how many heads will I see? It's the exact same question. How many heads will I see? You still cannot tell me whether I'm going to see 0 heads or 1 head, okay? Because this is a random variable. So we do not know the outcome for any one instance of a random variable. but we can understand a little bit about it. We can say, well, it will have 0 heads with probability of 0.5. It will give us 1 head with probability of 0.5. How many children will the family have until they have the first girl? We don't know. We don't know, okay? They might have to go have 4 children before they see their first girl. Or they might have a girl on the first one. We don't know what's going to happen, but we can have with certain probability, okay, we can understand what the likely outcomes are going to be, what's going to be likely and what's less likely, okay? And so this is what a random variable is, okay? We don't know exactly what number is going to appear, but we can understand which numbers are more likely or less likely.
So then it seems like from the data, then the more kids you have, actually no, it's not.
Okay, so this actually is not data; it's a model. It's a model.
A model.
Yeah. So we haven't actually found families like this, and we say, okay, go at it and tell us how many kids you had. All right. We didn't do this. This is just a model of what could happen.
So it's like a template of possibilities.
Right. It's just representing what could happen, and actually it tells us the probability of what's going to happen. Okay. So and of course when you flip a coin, it's not going to always be heads or tails with 0.5 probability, right? You saw this when you did your lab last week, and you saw, you flipped the coin 10 times, maybe you saw 7 heads, okay? Sometimes that's going to happen. You have a bunch of families that have this child numbered children policy, and some are going to have 1 and some will have more, and it might not follow this exactly, but this is the model of what theoretically should happen. All right. So this is just to explain the concept of a random variable. Okay. This is the intro topic, so we can't spend too much time. Okay. All right. What if I said, what's the probability of that a family is going to have 2 or 3 children in order to have their first girl? What's going to be your answer? Yeah, if I said, what's the probability that a family is going to have 2 children or 3 children, you would take this number and add this number. Okay?
Add them?
You'd add them. Because why? They're mutually exclusive. All right? And with mutually exclusive events, you add them when I say or. Okay? So, see how we needed to learn the awful rules of probability last week to kind of get to our things this week. This kind of stuff happens, right? So we had to learn this multiplication stuff and things like that. All right. So this is when you take on full, whole number examples or only certain values as the results. This is known as a discrete random variable. The other kind of random variable is a continuous random variable. There's a question. Yes.
If you add 2 figures and it's supposed to be 1 and you write 100%, is that fine?
Yeah, 100% is 1.
Yeah.
Okay, so either answer is perfectly valid, 100% or 1. That's fine. For the for the exam next week, be prepared to see either or, right? Maybe you write down in your calculations, you write 100%, but 100% is not in the answer choices because it's multiple choice. But you see 1, so pick 1, okay? Maybe you come up with the answer is 0.25, but then the answer choice has 25%, okay? So, you're going to have to be a little bit flexible, but I don't think that's unreasonable. All right, so on the other hand, we have continuous random variables. And these, the answers can take on decimals and or just any possible values. Okay, so the answers can take on basically, yeah. This is not the technically correct answer, but it's simple enough that we can understand. Okay, our answers can take on basically decimals, right? And so here's an example. One is, I could say let me pick a random person. Okay, so again, if I'm picking a random person, we have no idea who that person is going to be. Just like when I flip a coin, I have no idea what the outcome is going to be. When I pick a random person, I have no idea who that person is going to be. But I could ask, how much is this person going to weigh? How much does this person weigh? So, example. Pick a random person. So let's just say we pick a random man. Just to simplify things a little bit easier. Random man. How much does this man weigh? Okay. And just imagine we have the most accurate scale ever. Okay. So if you go to like Walmart and you pick up a scale, it might say you weigh 160.8 pounds or something. Okay, they could give you some level of precision, but not much more than that. Okay, but let's say we had the most accurate scale possible. The answer for one day, so one particular person, possible answer could be 168.2467 pounds or something like that, right? You can imagine that, okay? And maybe we pick this person's twin brother. And we say, how much does this person weigh? And this person weighs 168.3348 pounds. Okay? So these are different, they're different numbers, okay? And we could, I mean, they would round off to the same, but I keep all of these decimals here to illustrate that we can take on, there's a continuous range of variables, okay? Alright, so, but even though it's continuous, and technically there's infinitely many possible values that somebody could weigh, at the same time, even though somebody could weigh, you know, almost any possible number, we know certain weights we will not see, right? We will not see 0, okay? We will not see anything negative. We will probably not see anything over 2,000, okay? All right, so if somehow in your computer you have somebody recorded as 2,800, you know something went wrong, okay? Okay. So either there was a typo, somebody accidentally hit the 0 key an extra time or something, okay? So if we see something like that, we know that's no good, okay? Can I create a probability table for this? The answer is no, I cannot, okay? Because I would need to list off every single possible value that somebody could weigh. And I simply cannot do that, all right? Because if 168.2467 is a valid value, 168.2468 is a valid value, and 167.2469, and 160, whatever, okay, you get the idea. There's just too many to possibly list out to create a probability table. So instead, I have to represent this with a curve. And this curve would look something like this. Okay? So rather than, and this bottom line is supposed to be flat. Sorry, it's not, but it's supposed to. Okay? So, so not a table, but a curve. Yeah. And this represents weight. And so what this says is, what's the most, and you could just imagine, rather than just having a whole bunch of lines indicating all the possible weights, okay, we just have a smooth curve. this would be, you know, adult males and probably somewhere around. All right, so I'm just making up some numbers here, okay? And what this, so this tells us, what does this tell us? What's the most common or frequently observed?
160 or so.
Yeah, okay, so weights between 140 and 180 are probably the most commonly observed weights here, okay? So maybe this isn't adult men. Maybe adult men in another country or high school students or something, high school males. Okay? Whereas, you know, and we could say, you know, what's the probability that somebody is over here? Okay. What, if I were to shade all of the area under here, what do you think, what percentage would be represented by shading all of the area under the curve? 100%. 100%. Okay? So the total area under the curve is equal to 100% or 1. Why? What does this represent? This represents all the possible values that a man could weigh, right? So, if it represents all the possible, that represents 100% of the possible weights. Okay, so that's what we've got. All right. So if I were to so if I shaded this in, what percentage of everything do you think is shaded in here? Yeah, it's hard to say. I mean, but something around 35, 40%, something around there. So I'm just, with my eyeball, I'm just eyeballing a number. Okay, and I'm saying this region represents about 35% of what's under the curve. Okay? So I'll say about 35% is in the shaded region. Okay? And so that answer, that number is going to be the answer to what percentage of men weigh between 140 pounds and 180 pounds. About 35% of men weigh between 140 and 180 pounds. Okay? Or yeah, maybe it's closer to 40. I don't know. So I would say about 35% of men weigh between 140 and 180 pounds. Okay. Is the usage of this curve, does that make sense? Yes? Okay. So this is and so, you know, this is a curve that I just made up, and I just made up that number 35%. Okay.
But that 160 has nothing to do with this, right?
Oh, these numbers?
Yeah.
These were just random numbers that I made up to say, to kind of illustrate that it would be impossible to list off every single value that somebody could weigh. All right. Especially if you had a very accurate scale, it would be impossible to list off all the possible values, right? Sometimes we forget this because we're so used to dealing with whole numbers. But it's not like one day you weigh 135 pounds and then you instantly, if you gain weight, it's not like you instantly go from 135 to 136 pounds, okay? Somewhere between weighing 135 and 136, you weighed every single possible value in between, right? It's like the first lick of ice cream, you weighed two more grams, and the second lick you added, you know, a couple extra grams, and as the day went on, maybe you burned off half a gram of something, but your weight is not like you jump in these. Even though you might say I weigh this much, you don't weigh exactly that much, right? Okay. And everybody rounds their weight off to the nearest 5 pounds anyway, so. Usually down or up, depending on your gender. So, okay, using stereotypes here. All right. Okay, so this was a curve where I just made up kind of some numbers here. Okay. What we're going to deal with is a very specific curve called the normal distribution or normal model. And again, this represents a random variable which represents the outcome of a random experiment where the output is a number. Alright, look at that. That's beautiful. This is a normal model, and this is symmetric, okay? It's symmetric and unimodal. Right here, what value goes in the middle?
0.
The median, and because it's symmetric, the median is equal to the mean. Thank you. Great. Okay, so in the center, I'm going to put in the mean, and the symbol that I use for the mean here is mu. Okay, it's not going to be x bar or y bar, and the reason for this is because it's a model. Whenever we're dealing with models and not actual data, we use Greek letters, okay? Just to be fun, right? And this is the Greek letter for M for mean, okay? But it looks like a U with an extra line, but that's the mean. It goes in the middle. If I were to draw a line down the middle and shade half of this, okay? Or I mean, shade over here. How much would be shaded? 50% or 0.5. Okay. So if I shaded this, I would have 0.5 over there, and I would have 0.5 over here, right? And if I shaded the whole thing, that would be 100% or 1. All right. There's something interesting. Let me erase these 0.5 and 0.5 here. Okay. The normal model, if we figure out the standard deviation, okay, or actually the standard deviation will often be given to us. Okay, do you remember z-scores? What was the z-score?
How many standard deviations?
How many standard deviations away from the mean? Okay. So what is the z-score at the mean? 0. My z-score is 0 at the mean. And if I go up 1 standard deviation, okay, so the distance from here to here is 1 standard deviation. What's my z-score here? 1. Okay, simple enough. And if I go up another one,
Minus. Oh, sorry. Sorry.
I would have a z-score of 2. So these are z-scores along here. And this just says the distance from here to here is 1 standard deviation, and the total distance from the mean is 2 standard deviations. And I do the same thing going the other way. So what's my z-score here?
Minus 1.
Minus 1. And over here, minus 2, minus 3. Each of these, 1 standard deviation away. All right. So here's a... If I just shaded it from here to here, how much do you think is shaded?
5%.
5%? That's a good guess. Okay. The answer is about 2.5%. Okay. Now how? Okay, 2.5%.
Just go this over.
Huh?
I got it right.
I got excited.
You said 2.5%?
I
I
said
said
5.
5, and then
You said
you said
five.
it was kind of close.
Yeah. Okay. It's about 5, but it's 2.5%. Okay. Now.
Is it always 2.5%?
Well, okay. So we'll talk about this, and the answer is yes. Okay. So, as long as you look at a normal model in terms of z-scores, these numbers will always hold up. So I said there's about 2.5% here. Okay. So that's how is that represented as a decimal point? 0.025. 2.5%. About. I gotta say. So if there's about 2.5% here, how much do you think is going to be over here?
Same.
Same amount. Whatever's over there has got to be over here because it's symmetric, right? So about 2.5%. So if I got about 2.5% here and 2.5% here, how much is in between -2 and +2?
So it's like add those two minus 1.
Yeah. So what do I have left? About 95%, right? So about 95%. From there to this.
0.025.
So no matter the z-score, it's always gonna
All right. So this is where we've got to use a table.
Oh yeah.
All right. So go to the back of your book and turn to page A2 and A3.
Professor,
Yes.
so is it always, if you use z-scores, but no matter the standard deviation, it's always gonna be that amount?
Yeah. This is why z-scores are so important. Okay.
But no matter what the standard deviation?
No matter what the standard deviation is, if you turn it from numbers into z-scores, these numbers will always hold true. Okay? So if you go 2 standard deviations below, so if you have a z-score of -2, the distance beyond there is about 0.025 always. Okay? As long as we're dealing with a normal model and z-scores. Okay? So as long as you use normal model and z-scores,
Will we always be dealing with
A2
normal
and A3.
models?
no, I have to tell you that you're using a normal model and z-scores. You can't, if we were dealing with weight, it's not a normal model. This doesn't work. Okay? Yes. Okay. Okay. So I just told you. I'm just telling you for a fact that there's about 2.5% in this little triangle wedge right here. Okay? Is that all right with you? Okay. So I got 2.5% in this triangle wedge here. I've got another triangle wedge over here. How much is going to be over here? Okay. It's symmetric, right? So if I got 2.5% here, I'm going to have 2.5% here. Okay. So how much is in total of the 2 triangle wedges that I got? 5%, right? I'm adding 2.5% and I'm adding 2.5%. I'm getting a total of 5%. Okay. So if 5% is accounted for in these 2 triangle wedges, how much is unaccounted for in the middle? 95%, because everything adds up to 100%. Okay? No, but that was a great question because that's how you're going to have to solve a lot of these problems. You're going to have to kind of use this puzzle piece logic where little pieces, we know how much is over here, so that tells us how much is going to be over here. Things like that. Okay? So anyway, as long as we use the normal model or the normal distribution, and z-scores, okay, the areas under the curve can be found with a table. So turn to page A2 and A3 in your book. we got we have a normal table, okay? So this is the normal table I'm going to put in your test, which is very, very similar to this thing, but it's not exactly the same. But but you use it in the exact same way, okay? It's just the only thing that has changed is what has changed?
Something similar.
They're like exactly the, oh, I know. So on A2, the numbers are on the left-hand side. Okay, there's a column that says Z, all right, and it's on the left-hand side, all right. And then on A3, it's on the left-hand side. Okay, the column that says Z is also on the left-hand side. On this one, on one page, Z is on the right-hand side, and on the other page, Z is on the left-hand side. Okay. Other than that, it's exactly the same. All right. So don't stress. Huh?
Is that the table we'll be given?
Yeah, this is the table you'll be given, and I like it because it goes to negative 3.9 rather than 3.4. Whatever. Okay. All right, and this is what it looks like. Okay. 0.0, and this is it should look just like this on your. Okay, so this is the table on page B3, okay? All right. So, okay, just again, what at z-score equals 0, I'm right here at the mean, right? Right. If I draw a vertical line right here, and I shade everything to the left, how much is going to be shaded? 50%, okay, or 0.5. So when you go to your table and you look at that very first number, we have 0.5000, okay? What if I didn't draw a line at 0, but I drew a line at 0.01, okay?
So it'd be 50.
Now how much is going to be shaded to the left?
So it'd be 0.5398.
Okay? It's going to be, whatever it is, it's going to be just be a tiny bit more than 50%, right? Because I've just added this tiny little sliver into our thing, okay? So 0.01 is that area is 0.5040. The amount that's shaded to the left, 0.01 is 0.5040. Okay? It's the next number. It's the next number there.
So it's not 5, so I saw it differently.
Yeah. Okay, so I'm going to explain how to use this table, all right? So don't worry. Okay? And this is, this is here, let's just zoom in. Let's zoom in on the table here, okay? So so here's the top of our normal curve. This is 0. And this is where your decimal knowledge is very important. This is going to be 0.01. And that's very different from 0.10. 0.01 is very different from 0.10. Okay? So if everything to the left of 0 is 500, if I shade everything to the left of 0.01, I have just a tiny bit more. And if I shade everything to the left of 0.10, I have even more. How much do I have to the left of 0.10?
Left.
Yeah, so if I shade everything to the left,
0.600.
not 0.600, okay? We're going to look at our table. No?
What are you looking for?
0.10, 0.10. It's on the table.
So
Okay?
wouldn't it be 0.5398 minus 1?
No, it's going to just be 0.5398. Okay, don't make this any more complicated. Don't make it any more complicated.
Can you explain that?
Oh, right.
Yes. Okay, so I'm going to explain everything because the first time you use this table, it's gonna feel awkward, but then you'll get used to it, okay? Okay, you just have to think, all right, if I were a publisher, okay, and I wanted to create a table that was useful, all right, I could list off, you know, how much, if I draw a line and I shade everything to the left of 0, 0.00, how much is to the left? The amount to the left is 0.5000. If I want to shade everything to the left of 0.01, it's going to be just a little bit more than that. It's going to be 0.5040. If I shade everything to the left of 0.02, how much is going to be to the left of that? A little bit more, 0.5080. Okay, and it goes on and on and on, and you can see that this is going to have a very, very, very long table. Okay, so in order to kind of minimize how much the table is going to take up, they said, well, look at this. We're going to just make a grid rather than just one giant column, okay? And people are just going to have to use their brain a little bit. And if I'm saying, if I give you a number like 1.14, you're going to have to look that up by going to the row 1.1 and the column 0.04, and the number at 1.1 and 0.04 is the number that corresponds to 1.14, which is 0.8729. Okay. And if I give you the number 0.10, you're going to have to go to the row 0.1 and the column 0.00, and you get 0.5398. And 0.12, you go at the row 0.1 and the column 0.02, and you have 0.5478. All right, is that okay?
Yeah.
Yes.
All right. How much is to the left of negative 0.54? So how much is to the left of negative 0.54?
0.2946.
Okay.
Say that again?
So if I draw a line at negative 0.54, how much is to the left?
2946.
0.2946.
Okay, 0.2946. Great. What does 0.2946 represent?
The percentage of that shade.
5.
It's the area shaded to the left of negative 0.54. So if I draw a line at negative 0.54, it's the area shaded to the left. What is
Area
negative
shaded to the
0.54?
Area shaded to the left.
Negative 0.54 is a z-score. And what is a z-score? The number of standard deviations I am from the mean, okay? So here I am negative 0.54 standard deviation. So I'm almost a little bit more than 1/2 of a standard deviation below the mean. So if I draw my normal curve, in the middle I've got 0, and I'm drawing a line at negative 0.54, and if I shade all of this in, the amount that I've shaded in
Is it in the
is
table?
0.2946. Is that okay?
Yeah.
Is that good? That's not okay? No. This is using the table. All right. Okay. All right. And I'm sorry, I forgot your name already. Yes. Sarah. Okay. So Sarah, are you able to associate negative 0.54 to 0.2946? No. Okay, that's all right. Okay. So what you need to do, all right? So Sarah, on your table, either so sometimes the z-score is written over here, and sometimes it's written over here. Okay. One of the rows, you're gonna look up the row negative 0.5, and you're going to find the column 0.04.
I got it.
You got it, okay? And the column, the intersection there is negative, not negative, but 0.2946. And that represents, here's a normal curve. The mean is at 0, right? The z-score at the mean is 0. if I draw a line where the z-score is negative 0.54, the area to the left is 0.2946. How much is more than negative 0.54?
Just over 70%.
Yeah, the rest. So how much is that? Huh? 0.7054. Okay, so I do 1 minus 0.2946, and I get 0.7054. Okay.
That's the rest of the curve,
This
right?
is how much is greater than negative 0.54. This is how much is greater than negative 0.54. Okay? If you're rocking this out, okay, I'm going to give you maybe a hint for a shortcut, but and I'm just going to say it once, if it doesn't make any sense to you, don't worry about it, just stick to this, okay? Because it's symmetric, the area to the left of negative 0.54 is equal to the area to the right of positive 0.54, okay? Likewise, the area to the right of negative 0.54 is equal to the area to the left of positive 0.54. So if I wanted to know 0.7054, well, an equivalent number I could look up is positive 0.54, and that's going to give me 0.7054 because the table is symmetric. You can try this out and see for yourself. If what I said right now just didn't make any sense, don't worry about it, okay? You don't have to make your life any more harder than it needs to be.
Sorry, but the 0.7054
Yeah.
is
The area, if I were to shade,
that's
instead of shading to the left, if I shaded to the right of negative 0.54.
the remaining area that's not shaded will
Yeah,
be
the remaining area that's not shaded right now
Is
in this picture
0.7.
is 70.54%.
It's because you minus it by 1.
I subtracted
And that's greater than.
negative 0.54. Okay?
Correct.
Let's take a break. We'll come back at 9 o'clock.